So after finishing some intense learning units on equilibria, we return to some more qualitative pieces and then quantitative pieces that deal with energy. So more concepts on thermodynamics. So the first skill in this learning unit is on the second law of thermodynamics, which deals with the concept of entropy. So we're also going to learn about what makes a process spontaneous and thinking about reaction spontaneity. And when you think of something that's spontaneous, I want you to think about going downhill. Chemistry happens so that things become lower in energy. That's kind of the direction where things want to go. So spontaneous changes are things that we can think about that occur under a certain condition without the additional input of energy. So we're going to talk about both physical changes and chemical changes here. But as we think about this example of a physical change, we can think about the freezing of water into ice. And so that is a spontaneous process. That happens without the additional input of energy from the outside system. That actually goes downhill in energy. And I know it's a little bit weird to think about, but energy is actually given out into the system when something freezes. We remove heat in order to have that process happen. Some processes are still spontaneous, like combustion or even fuel metabolism in your body, but that requires a push to have it get started. But once that process kind of begins, we don't need to continually put energy in. So we're not talking about sort of spontaneous combustion here, right? You actually have to do a little bit to get that process started, but then that combustion process continues. So when we think about the first law of thermodynamics, we learned about that back in Unit 6 in Gen Chem 1, and that was thinking about enthalpy. But the first law of thermodynamics states that energy cannot be created or destroyed. We simply convert it into alternative forms. And as a thread throughout this learning unit, we're going to be talking about the burning of a candle that's going to provide heat that melts some ice. So we've got chemical and physical changes that are occurring in that process. So if we think about the physical changes that are sort of happening here, we're going to have heat is absorbed by this ice, and that's going to allow that lower energy ice to become higher energy water. So even though we think of melting as happening spontaneously, that's actually a process that goes uphill in energy. It doesn't happen unless you provide energy to have that go uphill. However, the chemical changes that happen here will provide that energy. The combustion of the wax in that candle, combustion meaning combining with oxygen, they generate lower energy products such as carbon dioxide and water, and the extra energy is given off as heat and as light. And so the heat can be then used to drive the process of that melting of that ice cube. So we're going to talk in this learning unit as well about this coupling of processes so that you can have something that goes uphill that's powered by something that goes downhill. So this learning unit is fairly qualitative. There are going to be some quantitative pieces that we do, but a lot of the questions that we're going to address might simply be thinking about or rationalizing why things happen. So reviewing what we learned about with enthalpy. So this again is something we learned last semester. It's the letter H to think about enthalpy. I want you to think about heat. I want you to envision bonds and intermolecular forces, and a process that is favorable releases heat or it makes bonds or intermolecular forces. Those are favorable processes. Those are processes that go downhill in energy. If you're releasing heat, that means because your system is being lowered in energy and the excess energy is given off as heat. So we can think about physical changes having enthalpy changes, right? We've talked about the delta H of fusion, right? So when we have the freezing here, that's actually where delta H of fusion is going to be negative. That's going to be heat that's given off. That's an exothermic process. Whereas if we want to melt ice, that actually requires us to put heat in. So that is going to be a positive delta H. That's an endothermic process. We also can have physical changes like the dissolution of a salt. Sometimes dissolving salts in water will make the water colder or it'll make it warmer. In this case, ammonium nitrate is going to make that water colder. And so this is going to be an endothermic process because that water gets colder because heat is removed from it to provide the energy to do this dissolution process. Chemical changes also have enthalpy to think about. We've done a lot with this, right? Hess's law and all of that, thinking about the delta H of reactions. We can have reactions like combustion, which is exothermic being a negative delta H, or we also can have processes that are endothermic. And so one of the things that we'll reconcile in this learning unit is how can you have something that is an uphill reaction in terms of enthalpy happen spontaneously? And the reason is we think about the second law of thermodynamics. So the second law of thermodynamics basically says that processes that occur spontaneously occur in the direction that increase the entropy of the universe. So we're going to see an equation on the next slide that allows us to think about and calculate the entropy of the universe. But going back to our candle burning and ice cube melting sort of example here, when we think about some of the physical changes that we have, the entropy is actually increased when we have a very ordered system, when we have our solid in water, and it becomes much more disordered as a liquid. That's actually an increase in entropy. So some of the qualitative things that we'll need to do is evaluate either a chemical reaction or a system or a process and ask whether the entropy is increasing or decreasing with that process. We think about entropy changes with chemical process as well. We increase the entropy of our system here when we have fewer numbers of reactants create more products with carbon dioxide and water. So when we think about entropy, there's going to be some words that we'll use to help us explain that. So when we think about sort of the entropy of the universe increasing, right? We need to think about the fact that there's multiple things that can contribute to this energetic downhill, if you want. Enthalpy is an important contributor to spontaneity. We said, favorable processes give off heat, are exothermic, but that alone cannot be a determinant because we can have both exothermic and endothermic processes be spontaneous. And entropy is the second term that we're going to be talking about. It also is an important contributor to spontaneity, but this alone cannot be a determinant. Reactions that may be unfavorable from an entropy standpoint may still be spontaneous. So when we really think of this delta S of the universe, that is what's going to end up always being favorable. Now this is going to be both dependent on entropy and enthalpy. So we can see here that it also depends on the delta H of the system. And here's how this comes into play. So the entropy of the universe has to do with the entropy of the system and the entropy of the surroundings. And we can substitute in the entropy of the surroundings here as something that has an enthalpy and temperature component to it. So what we can see is that the entropy of the universe, which is always increasing, is dependent on entropy, enthalpy, and temperature. And that's going to be an important piece that will come into play in our next learning, or our next skill here. But a couple of nuts and bolts for us to think about in this last slide here on this qualitative piece to think about entropy. So entropy has the letter S. And when you think about entropy, I want you to think about disorder. I want you to think about and envision the phrase more molecules moving more. If we can make more molecules and make them move around more, we're increasing the entropy. So processes that are favorable are going to make more molecules or allow those molecules to move around more. Okay? So if we think about these processes here that we know were endothermic processes, so these happened spontaneously, but it wasn't because of enthalpy. So entropy must be helping here. Entropy must be favorable. And we can see here in the melting of water, we take very ordered solid water and make it into disordered liquid water. We take a salt that's in a very ordered crystal lattice and we make lots of ions that are in solution. And even in this case where we have the decomposition of N2O5 here, we create more molecules and we make gas molecules, which certainly move around more than a solid. So in every one of these cases where we have an endothermic reaction, the chemical entities, whether they're atoms, molecules, or ions, have more freedom of motion. After this change happens, we've increased their entropy, and that increase in entropy helps to offset the fact that enthalpy was not favorable. So what are some of the kinds of problems you're going to see with regards to entropy? Well, you might have to think about predicting the entropy of either a reaction, a process, a system, right? So here's some tips for how you can think about those problems. Larger molecules, whether it's more atoms, larger atoms, longer bonds, have more entropy. So if we're comparing these two, for example, CF4 or CCl4, CCl4 is going to have greater entropy because bigger molecules with chlorine versus fluorine, longer bond. If you increase the temperature of your system, you're going to give your system more entropy. So in this case, seawater at 23 degrees is going to have a greater entropy. Gas or phase changes are going to always increase entropy. So going from solid to a liquid to a gas is going to be increasing entropy. So even for the unfavorable enthalpic process of melting an ice cube to make liquid water, because we're going through that phase change and we're making something that's more disordered, that's increasing in entropy. Dissolving salts, again, increase that entropy, taking a very ordered crystalline solid and making it into very disordered ions. And creating more gas molecules, so that helps explain and offset the unfavorable enthalpy that we have here, because we make more molecules, and specifically we make gas molecules. So you might see some qualitative problems asking you to predict which system, state, or side of a chemical equation has the more favorable entropy. So quantitatively, we begin reviewing some of the things that we've talked about before. We've done Hess's law before. We've done delta H of formation. Do you remember? That's where we imagined taking all of our reactants and breaking them apart into their elements and then reforming them into their products. And the difference between these two is going to give us the delta H of a reaction. And that's where we saw this crazy equation, right? Where it looked like this, and we had to use Appendix B, and we basically needed to sum up, it's always products minus reactants, we needed to sum up the total enthalpy values of our products and subtract the enthalpy values of our reactants, and that would give us the overall enthalpy of that reaction. So this is a pretty easy skill here, because all we're going to do is use a different column in Appendix B. So if you haven't had a chance, go onto the Resources tab and look up Appendix B and remind yourself that, oh yeah, I remember using delta H values here. Well, now in this learning unit, we're going to use delta H, and we're also going to use the delta G values. And that's it for this first skill on entropy.